Now, as a practical sort of way of making this work, usually you see this kind of titration experiment. It's this classic notion that sitting down in this beaker is something I don't know. It's a particular amount, maybe it's 8 protons. But actually, because it's in liquid, I can replace this moles of acid with instead the idea of a molarity of the acid times the volume of the acid, because molarity times volume will equal to the number of moles. And since I know the volume that I decided to put into the container, I knew this amount, then what I'm actually going to be calculating is the molarity of the protons. Now that will be equal to the moles of the hydroxide, to the moles of the base that titrates it, at the point that I have achieved equivalence. Well, you can see how I can make this experiment work if I know how much hydroxide I'm titrating. In this particular case, because I know the concentration of the hydroxide to start, and I know how much of the hydroxide I added as volume, then I have 3 values that I know. I know the 2 volumes, I know the concentration of the hydroxide, and the only thing left that I don't know is the molarity of the protons. Looking at this picture again, just to fully understand it, I know the volume of the hydroxide, excuse me, of the acid, because that's how much I decided to pour in there. I know how much the volume of the hydroxide is that I added, and I know the concentration of the hydroxide, because that's the solution that I made up. The only thing that is unknown is the amount of the acid. So by knowing these 3 things, I know this. If I can find the point where the moles of acid is equal to the moles of base. At this point, I've only given you one way of being able to find this indication. It's whether my hand gets chewed off or not. But in a second, I'm going to show you a new strategy for how to do that using chemical indicators.